Согласно традиции, я в очередной раз представлю доктора Гамини Суманасекера, наш старый коллаборатор и старый друг. Он здесь уже четвертый раз, и множество людей из нашего университета поработали у него в лаборатории, не просто побывали, а поработали. Роман Сергеевич положил тропинку, Ульяна нет, остальных кто был первый. Очень сложно, Алексей там провел пару незабываемых лет. И доктор Гамини, он, конечно, выдающийся ученый. Он может посмотреть на его как схерша, но правда в Америке мало кто знает, что это такое, он не ориентируется. Он закончил аспирантуру в сильнейшем университете в Америке. Потом лет 10 он перебрался в университет Луисвилля и участвовал в создании открытия нового центра, института, громадного института, для источников энергии, новых материалов. Это громадный институт с десятками исследователей, с сотнями дисциплин, в общем, и у него он стоял у истока этого института и занимается вещами совершенно всегда новыми, революционными. Когда появился графен, он был один из первых, кто со своей группой, кто в эти исследования влился. У нас с ним общий грант, ник, да, малый инновационный международный исследовательский, даже не знаю точно название, но он свидетельница хватает. В условиях этого гранта они должны разговаривать на передаче, мы очень рады и прочесть каждый раз в общей сложности 5 лекций. Одну из них мы попросили сделать как можно более простой, понятной для сегодняшнего. Ну и все следующие, они с точки зрения математики, конечно, все очень просто, но они, возможно, будут более детальными. И написано было совершенно неправильно, что был синхронный перевод. Никто из нас, конечно, не в состоянии заниматься синхронным переводом. Он будет рассказывать медленно, что-то непонятно было, мне кажется, не каждое слово. Вы переспрашиваете и Роман Сергеевич, и Данила, и экспериментатора, и Роман Сергеевич, да, должны будут вам помочь. Но, и я уже совсем не подхватил, но я сомневаюсь, что я что-то могу сказать больше, чем Роман Сергеевич. Гамини, спасибо.
Thank you, Victor, for the introduction. I didn't understand most of the stuff. So, today I'm going to talk about Phosphorene as a new material. It's like graphene, two-dimensional material. So we are going to study some new properties and new physics of this material under some exotic conditions. Mostly we are going to talk about under extreme pressure. So what's happening in this material? So,
во-первых, непонятно. Сразу задаем вопрос, не ждем паузу, надо сохранять ясно. Речь идет про фосфорин. Это аналог графена. Графен, по-английски будет графин. Будете с графином. Сразу учите, что графин это там наливают на тот самый двумерный плоский материал. И речь пойдет о свойствах фосфорена, в основном и условиях
So this project is actually recent grant we got from Department of Energy and also supported by Center for Renewable Energy. So in this project we have Dr. Jasinski and Professor Minyu as the OPIs. Then I have these 3 students. They are working on this project, and the last 2 they already did some work on this, and now they graduated. One is working at Intel and one is a postdoc at University of Illinois at Urbana-Champaign. So let me first introduce some of the two-dimensional materials. So everybody is familiar with graphene. So that is all carbon atoms in a two-dimensional structure. So then if you attach hydrogen to graphene, you can make it something called graphene. So these are actually two insulators. Then we have something called hexagonal boron nitride. That's a good two-dimensional material. And also some niobium diselenide, molybdenum disulfide. These are some of the more popular two-dimensional materials. They have very different properties. Then here I put this kind of logos. That means these are good, we call building blocks for different structures.
На слайде несколько разных двумерных материалов. Графен самый простой, то есть слой атомов углерода. Если мы к этим атомам добавляем водород, получается графан. Также есть нефрит бора, селенит неофия и еще другие структуры. Все они обладают разными свойствами, и все они могут быть building blocks, строительными блоками, как лего, для создания разных других материалов функциональных устройств.
So let me first show you, everybody familiar with graphene. So starting from graphite, if you can separate one single layer, you have graphene. So Andre Grime and so they discovered the first graphene. So then they got the Nobel Prize in 2010 for the discovery of graphene. You can see graphene has very exciting properties. They are extremely strong, so even you can block a bullet. So they are used for this conducting transparent electrodes. You can make devices from those materials, the graphene material, and also they are extremely light. You can see a pellet of graphene supported by this tiny stencils here. So graphene has a lot of applications. So starting from conducting ink, then you can use for like different sensors, light emitting diodes, some composites for different structures. So then also in the energy sector we use graphene for solar cells and batteries, supercapacitors, then touch panels for flexible displays. So many properties of graphene can be used for many applications. So here are some of the applications in the pie chart here, what they are used for different applications here. Okay. So now question is, why do we use 2D materials? So we know if you look at the density of states for different quantum sizes, we have something called the quantum size effect. For three-dimensional material, we know our density states as the square root of E behavior. If you go to two-dimensional structure, they are more like constant. We have step functions. One-dimensional materials have this 1 over square root of E behavior. Then if you go to zero dimension, we call the quantum dots, they have more like delta function kind of density of states. So these have different properties going from 3 dimension to 0 dimension. So here we are mostly going to talk about these 2-dimensional structures. So that's one aspect of why we use 2D materials. That's another thing is 2D materials are very important to study something called the interfaces. If you have two materials making interface, if you have 3-dimensional material, we know our thickness is changing throughout the material. You see here one thickness, when you go to different position, you have different thickness. But if you have a 2-dimensional material, they are very uniform throughout the material. So that makes it more interesting to study the interfaces. So here also you can see, depending on this thickness of the 2D material, your mobility can be changed. So you can see when the mobility given in centimeters square per volt second, you can see how depending on the thickness, how the mobility is changing. So So they are not extremely large numbers, but compared to gallium arsenide, this is a reasonable mobility number. But much smaller than the graphene number. Graphene has much higher mobility. So also you can use this one in electronics. If you use, this is your material here. So this can be any 2D material. Then you can have your source and drain, and you can have your dielectric and the top gate, or you can, if you want, you can have bottom gate. So then you have something called a field gate transistor based on this 2D material. So what is most important thing is these 2D materials, if you change the number of layers, you can make it extremely interesting. Suppose in the bulb, this is we call the indirect band gap. So again, 4 layer indirect, 2 layer, but when you come to 1 layer, this becomes direct band gap material. So that can be very useful for optoelectronics properties.
Идет что-нибудь понятно? Хорошо. Тогда немножко про все сразу. Речь идет про то, что в нуклеарных материалах есть определенная плотность электронных состояний, которая определяет свойства материала. Это как раз про них, это лестница.
Density of states here.
Yeah, density of states. Чем он еще хорошо? Вот если мы возьмем обычный материал, он толщина меняется, там натрий, все равно меняется. Примерно она всегда одинаковая с высокой точностью. Там нет разорванных связей, данный бond и данный бond — это разорванные связи, и их можно закрыть, это будет совершенно поверхность. Но самое интересное, по словам профессора Суманасекера, это возможность регулировать ширину запрещенной зоны, меняя число слоев октября. Ширина запрещенной зоны, например, то, на какой длине волны излучает ваш лазер. Те, кто работает с лазером, знают, что некоторые длины волн получают очень трудно. И эти материалы способны дать нам то, что надо, потому что можно регулировать ширину запрещенной зоны. И для транзисторов, да.
This field gate transistor here. So we'll talk about that later. So there are a lot of different 3D materials. So if you start from graphene here, so graphene has no band gap. So if you look at here, there's no separation here. It's like 0 band gap. Then we can go to so we call this is a semi-metal because there's no band gap here. But if you go to some materials like chromium oxide, these are also 2-dimensional materials. They are more like half metals. Half metal means in the spin one direction can be conductive, but the spin down can be insulating. That's a half metal. So then you can have metals like vanadium oxide, vanadium sulfide. Then you can have a superconductor, niobium disulfide as a superconductor, still 2D material. Then this hexagonal boron nitride, that's a very good insulator. This has a band gap more than 5 electron volts. So then molybdenum disulfide, this tungsten disulfide, they are good semiconductors. Phosphorene also comes in this category, that's also semiconductor. These are, you can see different 2D materials have different properties.
All types of material.
Yes.
Insulator to
So exactly, yes. You start going from insulator to semi-metal. So conductors, metals, half metals, semiconductors, and we call it semi-metal. Is like there's no band gap here.
Понятно, да? То есть двумерные материалы могут иметь любые свойства в плане электрического транспорта, а высокосовершенных изоляторов до
сверхпроводников.
Сверхпроводников.
So then also depending on this, it's not very clear. Depending on these properties, they can have different optical properties. for example, if you take external boron nitride, so that has about 5 electrons, or they are mostly ultraviolet range. If you go to graphene, graphene has almost no band gap, so you can have a small band gap that can be in the infrared range. So depending on this, then you can have these other semiconductors, they have band gap falling in the visible range or coming to red or infrared, finally going to microwaves and to much higher frequencies. So depending on what you have your band gap, you can have different optical properties throughout the optical spectrum. No, so since your band gap is, so that can have properties in absorption or any related properties. So you can have, for example, the hexagon boron nitride can be used for some properties in these DVD players and things like that, because that's UV DVD players. So then if you take some of this graphene can be used for terahertz antennas and receivers. So then these things can be used in the visible light applications.
Получается, что двумерные материалы, кроме широкого спектра электрических свойств, также обладают широким спектром свойств оптических, то есть поглощают и излучают практически на всех длинах волн, ультрафиолетового, туннельного и инфракрасного спектра. И это может использоваться DVD, дисплеи, разные микроволновые приложения.
I have another slide to make it clear. So like I said before, these 2D materials can be used as building blocks for different materials. For example, if I start with graphene, you can have that's more like a metal, right? So semi-metal. Then you can go to semiconductor to insulators, more right here. So then I can have building blocks, these 2D materials for other structures. So if I draw quantum dots on graphene, so then I can have, graphene is a 2D material, the quantum dots are 0 dimensional, I can have structure of 2D to 0 dimensional material. Then I can draw nanowires or carbon nanotubes, then that is more like 2D, 1D structure. Then you can have even like 2D to 1.5. This is fractal dimension. So fractals, they usually in fractals you call like 0.5, 1.5 kind of dimension. Then you can have 3D, 2D. Like if I draw something on the semiconductor, you have 2D, 3D kind of. Then also 2D material. Any of these material you can draw one on other. So if you go graphene on this WS2, then boron nitride, I can make a series of 2D heterostructures. Yes. Sandwich structure. Yeah. This we call the vertically stacked, or you can have lateral structures also.
Okay, 2D material is like a base.
Yes. Then you can make different structures on that 2D material.
Ну, тут, наверное, все понятно, что материалы могут быть основой для выращивания на них еще разных структур, одномерных структур. Видимо, на них все здорово растет, то есть можно высокосовершенную структуру выращивать, если у вас высокосовершенная подложка. Очень
These are some of the more common prototypes of 2D materials. If you can go from this cadmium iodide, so to, if you go to, you can see making different atomic layers. You can start like making like 64 layers or come down to maybe 10 layers. If you go to graphene, you can have only one layer. So these are typical prototypes for different 2D structures. So you can make many layers depending on how. So this is not very important.
It's about the symmetry of...
Yes, yeah. So these are the crystal symmetry here, depending on the crystal. Still they are layered materials, but they have different crystal symmetry. So depending on that, you can see how many layers you can make. I don't think this is very relevant. I don't want to. So now to make these 2D materials, so one way to do is start with this layered structure and we exfoliate them. To exfoliate, what you do is, this is the bulk material. First you intercalate them with like potassium. So suppose this is graphite. So this is a 3D material. So then you intercalate with potassium atoms. So then you heat it. When you heat, they become kind of separated. So then when you put it in sonication, so they all disperse and make single layer. So this is called the exfoliation of this layered materials.
Выводы про то, что 2D материалы очень разнообразные. Есть, да, отложилось. Теперь я буду рассказывать, как получить этот самый плоский слой из объемного материала.
Any alkali metal, you can have potassium, lithium. Yeah.
То есть можно взять, например, графит, и вместо того, чтобы скотчем его много раз скотчить, можно взять камень, внедрить его туда, нагреть и разорвут атомную плоскость, и вы получите в итоге единичную плоскость. И сейчас мы будем много говорить о том, как еще получать примерный материал разных способов.
So the line sonication will make it similarly. You can see when this is this graphitic structure. So this structure is shown here. So still potassium is here. So after sonication, you see it's more like this single layer. Oh yeah. So that's the layered structure. All the layered structures look like that. It's more like papers in a book. So you are going to remove each page now. You have to start with the layered structure. There are many layered structures like that. You can see how this graphite XRDP is here. When you put potassium, you have this something called the C8. So then when you separate, you get like this. After sonication, you get this nice graphite. So if you look at the Raman spectroscopy, so graphite has this, we call it D band here. So that, G band. So then after integration, you have this new corresponding to this one. So this is after heating, you get this structure. So then you have Raman structure. This is for the perfect graphene. You have G band and also something called the 2D.
На левой картинке результаты рентгеновских исследований этих материалов графита один узкий пик, а когда он становится графеном, пик расплывается, потому что рентген не встает. А на правой картинке рамановские исследования, практические исследования. Гамини, could you explain some details of why?
Я буду объяснить. Самое важное обратить внимание на соотношение высоты пиков G-бендов и D-бендов. Мы видим, что на графит много слоев, G-бенд первый пик выше 2 D-бендов. А соответственно, когда мы получаем однослойную структуру, то у нас соотношение пиков меняется как раз по периоду, что мы получили однослойную.
So this is G band is a carbon vibrational mode. So this is a 2 phonon mode. So this is exactly twice of this 1300. It's coming around 2600.
G-бенд получается взаимодействие углерод-углерод,
Yeah, it's carbon. Yeah.
В одних это, по-моему, это есть.
Yes, exactly. Yes. Okay. So this, like I said, there are a lot of these layered structures. So these are some of the intercalation. So like I said, potassium going in, you can have any of these porous structures. So this is something called this zeolite. So you have this large mesoporous structure here. Then you can have something that has these channels here. All these pore structures you can put this intercalation in any of these pore structures. So for example, zeolite, they have this large pore, you can put potassium or lithium into that one. So these are any structure that you can easily intercalate material. To intercalate, you need to have a spacing, right? So this, any of these material are easy to intercalate with any chlorine atom. So these are some of the materials I showed here. So then to intercalate, you can have different ways, like you can have physical or chemical attachment. So chemical attachment more like ion exchange. You have to exchange and make positive negative charge. They will attach to the between the two layers. So or you can physical attachment. You just by vapor or some electrochemical you can physically attach the material. So after that you have to just exfoliate and remove the layers.
Здесь речь идет вот о чем. Если мы хотим уже имеющемуся полимерному материалу еще что-то добавить, чтобы изменить его свойства, то у нас есть такая возможность тоже. Во-первых, у полимерных материалов есть разные пор. Они могут быть и круглые, похожие на каналы, и всякой сложной формы. И туда можно добавлять другие атомы. И это будет менять свойства материала. А во-вторых, можно, как я сказал, химическим способом, то есть ионным обменом, или чисто физически напрямить что-то, внедрить структуру между двумя слоями имеющегося полимерного материала. Таким образом, мы еще можем усложнить структуру и получить новые свойства. Мы сейчас в основном именно об этом говорим, о том, чтобы управлять свойствами материала, как угодно его модифицировать, чтобы получить то, что нам нужно.
So okay, now I am going to move to Fosforene. So first we are going to talk about something called the black phosphorene. So if you look at phosphorene, so this is like graphene all carbon atoms, right? So in phosphorene, that's why it's interesting, these are all phosphorus atoms. So other materials, they have more than one atom, right? If you take molybdenum disulfide, they have molybdenum and sulfur atom. So here is everything is phosphorus, just like graphene, but structure is different. In graphene, they are all very plain, but in phosphorus, they are not very plain, they have something called a puckered structure. So you can see, if you look from top, it looks like this one. You have one atom above other atom. This is, if you the side, you can see it's more like. So in graphene, they are all just one. What's that? That's the stable structure. So that's how the phosphorus interaction happens. The minimum energy configuration cannot be yes. So you have to have get this stable structure. They have to make some distortion.
In this picture, the yellow and red.
They all are carbon, phosphorus. Yeah. So this one shows in more like in one plane. This one is slightly below. In carbon, they all in the same, right?
Фосфорен — это вот такая структура. Почему-то энергетически ей оказалось выгоднее стать не плоской, а разделиться на подслои.
So this shows the unique cell phosphorene with the translation. So this, if you look for like graphene, like I said, is all planar structure, molybdenum disulfide, so hexagonal boron nitride. This is just like graphene, hexagonal boron nitride. They are also planar. So, but they are not all carbon, right? Boron and nitrogen. But phosphorine, they all like they are this carbon structure. These are the phosphorine layer. These are many layers, right? You have to remove to get the. So this is phosphorus. So phosphorine is one layer of this one. So this also you can have. If you look at phosphorine, you can have actually two different kinds of structures. If you look from here, these are more like we call the armchair structure. Armchair is like your chair structure. Zigzag is more like going. You have something. Yes, draw here. Yeah. If you have something, this is more like zigzag. Sorry, armchair. Right? So if you have something like this is zigzag. So if you look from no, you can have both. If you look from side, you can have this way or this way. Yeah. So this one shows you if you look from this side. Yeah, here A, B, C, D, then I draw here A, B, C, D here. So you can see if you go in this direction, they are showing more like armchair. So if you go this way, the A direction, they are more like zigzag.
It's only drawing or?
Yeah, it's just a drawing, how you draw it, yeah. But you can cut the phosphorine to have that edge. That
Тоже понятно. Интересное свойство, что если мы посмотрим на него сбоку, то его боковая сторона может быть как кресло, шестиграннички, или как зигзаг. И это тоже может определять его свойства, если вы принципиаете какой-то атом. И вот сюда, или вот сюда, то это будет происходить по-разному. В зависимости от того, с какой стороны вы будете.
So, yeah, so this is what I was saying, like graphene, and also there are some other materials called silicon, that is silicon based, and germanium, that is like graphene is all carbon, right? So then you can have silicon and germanium and tin. They all are real 2D material, but these things cannot exist in free form. You have to grow on a substrate. So, but phosphorine we can have free because you can exfoliate. So that's what I'm trying to say here. Graphene, like graphene, phosphorine is a monolayer of a single element, right? Because of all phosphorine. Other 2D material like silicon, that is coming from silicon, and germanium, that's coming from germanium, and stannine, that is coming from tin. They need the substrate to grow. These are not very common.
All of these materials are exact.
Yeah.
But
Yeah.
phosphorine and graphene
Other
don't need the
nature, exactly. Yeah. Also, these things are not very common. Very few people have made those things.
Тут было понятно, что графин и фосфорен, они могут быть в свободном состоянии. Всем остальным они тоже существуют, но им нужна подложка, на которой им надо расти. Просто так, стойчиво, вот так вот не живет.
Okay, so another important thing is compared to graphene, this phosphorine has the bucket structure. Then also that has a very big anisotropy. That means your properties in one direction is very different from the properties in the other direction. Graphene is very isotropic. So this has very good properties, and also they can have tunable band gap and very high carrying moment, but smaller than graphene. So this is the one I think I didn't have a good picture. So now this one shows you more clearly the properties. Next one, boron nitride, band gap is about 6 electron volt. That's why they have properties related to ultraviolet. So graphene, they have almost 0 band gap. That's why you can find properties in terahertz frequencies. The other materials, they have smaller band gaps, so they can have properties in visible to yeah. Yes, yes, yes. Black phosphorus comes.
Exists white?
No. So typically, what you find is white phosphorus and red phosphorus. White phosphorus is very strong, right? They react immediately. They are very hard. So that's why black phosphorus is stable material. So that's I didn't put it here. So this the phosphorene we are talking about. So phosphorus has white phosphorus has band gap about maybe 0.3 EV. But if you go to phosphorene, you can get band gap about 2 EV. You can see how big range you can have band gap. Typically we are talking about phosphorus means white phosphorus. So this we already talked about. So this is the important thing. If you take phosphorene, so you can see going from 3 layers, 2 layers to 1 layer, your band gap is changing. So here you have 3 layers, you have this small band gap, and it's becoming a little bit bigger. If you go to 1 layer, that becomes almost like 2 electron volts. So you can see with the number of layers, you can change your band gap dramatically for phosphorene. So if you look at this picture, so if you take any other material, you can only change your band gap in these small ranges, right? But if you take phosphorus, you can change your band gap in a very large range, almost like 0.3 EV to 2 EV. So graphene you can only make very small range. That's why black phosphorus is more interesting. You can change the band gap with very large range. This one shows you how the band gap changes with number of layers. Numbers you can see how from bio to monolayer.
Про возможности управления шириной запрещенной зоны. Для большинства материалов это можно делать, но, как видите, для инженерных материалов у фосфора самые большие возможности для того, чтобы менять эту ширину, а значит менять свои свойства по сравнению со всеми остальными материалами, ну, видно, что в разы больше. А только если вы, может, дадите краткий комментарий, управляя шириной запрещенной зоны, какие самые важные свойства материалов можно менять и получать?
Можно получать разную степень проводимости. Практически понятно, но проводимость, потому что если еще возможно, изолятор будет проводимость, вот. И степень полупроводимости, так сказать, можно контролировать. В некоторых случаях, что проводники превращаются в проводники и наоборот,
Все получается, говорится.
Any question?
We have step change or tuning of
Tuning of the band gap. Yeah, depending on the number of layers. If you start with bulk black phosphorus, you have band gap only 0.3 electron volt. But if you go to 1 layer, it's about 2 electron volt. That's a big range. Right? Yeah.
quantum, and 3 in the ограниченный шаг.
No, this is
Yeah. We have a limited step for changing the bank, or it can be little.
yeah. This is how it theoretically it changes like this one here. You can see 2 layers, this much, 3 layers. You can see how continuously it changes.
Continuous.
Yeah. It is continuously. Yes. No. So it's more like this. Continuous. This is how the electronic structure changes. Okay, so this is, so you can see how the band gap changes. This is all for the phosphorene. So you can, by changing the number of layers, like I said, you can go from 0.3 to 2 electron volts. So, but also you can make it more by putting heterostructure. Like if you put graphene and phosphorene together, you can change it to graphene almost 0 band gap. You can make to even go to 4 electron volt if you make a heterostructure of graphene and phosphorene. So that's also if you dope with different materials, like if you dope with carbon, fluorine, boron, then you can increase more than this 2. Typically, you can go only from 0.3 to 2, but by doing heterostructures and doping, you can make even bigger change, and also making quantum size effect, nano ribbons, and putting some other edge effect, you can make more change in your band gap.
Еще раз, мы можем иметь такие значения ширины запрещенной зоны, а если мы слепим бутерброд из фосфорена с графеном, то получится на 4,25 структуры. А если еще допинг сделать, то есть добавить еще какие-то атомы, то получается еще набор целых значений, и также рыбный клеточек, да, если мы сделаем моноленты и еще сложнее малаж группами, то можно получить еще дополнительное значение ширины запрещенной зоны. То есть мы целый спектр покрываем достаточно часто. Okay?
So I will skip this one. So this is some of the properties, like I said. So this is another, some of the other properties I will quickly go through. So then also they can have this photocatalytic applications. So I will skip that one, so I don't have much time. So now, so challenges of making this phosphorene. So we know phosphorene also you can do by something called the mechanical exfoliation. That's how underground first discovered graphene, right? So you take the bulk material, put the scotch tape and remove it and keep peeling it off until you get one layer, right? That's how graphene. You can do same thing for the phosphorene also, because that's a layered structure. Use the scotch tape, remove many layers, then do it again and again, do like 100 times until you end up with one layer. That's we call the mechanical exfoliation. That gives you very high quality material but tiny in size, right? Only 1 micron size phosphorene, so that's not scalable. So, but liquid phase exfoliation, like put it in some like intercalate and exfoliate. So that way you can make large quantity, but material is not very high quality because you have other defects and other disorders. So then also people have tried pulse laser deposition. You just hit with the pulse laser, like nanosecond or femtosecond laser. Then you can deposit by this laser deposition. That also doesn't show very good crystallinity. So this is the best way to make, but small quantity. So these two are high quantity but poor quality.
свойства поговорили, что такой чудесный совершенно материал, теперь вопрос, как его получить. Способ геймового веселого работать. Можно взять кусочек скотча, поскотчить много-много раз и получите хороший слой. Но этот способ не масштабируется, то есть нельзя построить фабрику, где будут скотчем этот блок. Вот. Можно сделать жидкостное разделение, как было показано раньше, то есть атомы какие-то разрывают эти слои, либо можно это сделать с помощью лазера. Лазер материал вылетает и, видимо, осаждается в тонкий слой. Но последних двух методов так себе качество. Ну, зато они масштабируются. Лазеры можно, если только стоять много. А Гамини about the third type.
Pulse laser deposition? Yeah. So that's usually UHV system, high vacuum system. You just focus high pulse laser beam, then it just deposit onto the substrate. That way also you can control the number of layers, but they are not very high crystalline.
You have crystallinity, but not so good.
No, very good, yes. But good for some lab scale studies.
Лазером действительно это все распыляется, на какую-то подложку садится, можно хорошо контролировать число слоев или толщину этих слоев. Но сами слои получаются так себе, потому что он не вырос, не кристаллизовался как кристалл. Правда, мы туда упали, они как-то соединятся более-менее, но структура будет несовершенна.
So if you look at this synthesis methods people have done for graphene, and this is for the transition method like chalcogenide, these are like molybdenum disulfide, tungsten disulfide, tungsten diselenide, this method. Comparing these three, graphene can be done by this tape method, that's how they do it. Then they can do by exfoliation, lithiation, plasma, assisted growth. So then recently we all are doing some CVD growth of graphene, right? That's very easy to do. Then also hydrothermal synthesis. TMD also you can do all these techniques, but for phosphorene, so you, like I said, you can do by tape, you can do by liquid exfoliation. Lithiation has not been done, but recently our group, we did lithiation work, we recently published that work. So this, like, you can do pulse, but there is no CVD or no hydrothermal synthesis of phosphorene. If somebody can do that one, that would be very nice. We are also trying to do CVD growth of phosphorene, still we haven't been successful.
Some people have to take it.
Oh, sure. I can give you this presentation.
Share the presentation.
Yeah, I can give you this one.
Ребята, это открытая лекция, презентацию. Все, кто захотят получить, я полностью вышлю все слайды.
I give you the presentation. So that, but the biggest problem for phosphorene is they are very unstable in air. So if you expose to air, it degrades. So that's why biggest problem for phosphorene. So if you leave it, so you can see this is how AFM picture looks like after 3 hours. In 46 hours, you can see how the surface becomes pretty bad, the oxidation.
Looks like a pizza.
Yeah, exactly. So here you can see it's pretty nice. But, so that's why once you make phosphorene, you have to cover it with some cabin layer. So here, some people, once they have this, the BP is black phosphorus, then this is hexagonal boronite, right? You can cover phosphorene with boronite, right? Also, you can make it better if you have boronite right your underlayer. So then you have better quality when you put boronite right, then you put your black phosphorus, then you put another boronite right, and now you are tapping from both ends. So then it stays very nice. So there are some structures, they perform perfectly, just like regular 92.
Ребята, смотрите, получается материал чудесный совершенно, но он деградирует, воздух портится. И его нужно как-то закрывать, гексаметризированно, например, хорошо подходит. Excuse me, what type of, what's that about?
This one?
Yeah.
The same AFM, atomic force microscope.
Yes,
Yeah.
It's oxygen or other.
Yeah, I think it's mostly oxygen and moisture. That's what reacting with the oxygen and the water.
And water.
Yes. Because atmosphere always we have moisture.
Получается, вода и кислород, все такое. Окей.
So here are some of the work done in our groups. You can see when you exfoliate black phosphorus, so you get this kind of nice dispersion here. So this is how they look in SCM and also microscope, optical microscopy. You can see this kind of tiny layers. Atomic force microscope also shows mostly monolayer phosphorin here. So then if you look at the photoluminescence, you can see you don't see a big photoluminescence peak until you get to monolayer. So the bulk and Q layer you find not strong luminescence, but monolayer phosphorin shows your band gap comes close to 2 electron volts like we expect for the monolayer. So when you do this material, what we do is, I don't know whether you are familiar with the centrifugation, right? When you put in the centrifuge, only the heavy things deposit at the bottom. So when you take material from bottom, you get many layers. So this is so this is the Raman spectroscopy for black phosphorus. So when you take from the top, you get this. This means top you have mostly monolayers. In the middle, you get several layers because that's heavier, right? So you, depending on where you pick in your after centrifugation. So this is your centrifuge tube. So from the top, like bottom. So if you take from here, mostly monolayer. If you pick from here, there are mostly few layers. So if you take from here, it's more like very bulk, many lot of layers. Yeah, yes, yeah. It's a centrifuge. It's going like that. Always under gravity. They always sediment to the bottom. Like this is how we pick it here. So this is from the bottom. So this is from the top. This is from the middle.
Ребята, смотрите, это уже идут собственные результаты. Как видите, ссылки пропали, это то, что они делают уже в своей лаборатории. Они делают жидкостное разделение, и потом, чтобы частицы с разным числом слоев получить, делается центрифугирование, и в зависимости от того, откуда вы берете частицы, сверху или снизу, будет разное число слоев. Легкие оказываются вверху, так вот оказываются. И это как раз монолейер, то есть однослойные частички. Это, наверное, не очень трудно сделать у нас.
You can see this is a TEM picture of a single layer, like this one layer here. So this actually is scanning electron microscope, is a transmission. So this phosphorin has these 3 different modes. So we call this one A1G mode, this is B2G mode, this is A2G mode. That's coming from this symmetry, the group symmetry, right? These are the vibrational modes. You can see This is A1G, that is mostly in-plane vibrations. So this one, A2G, also in-plane vibrations. B2G, middle one is out-of-plane vibrations. You always see these three modes. You call it A1G, B2G, and A2G mode.
Особенности того, как это все видно в рамках спектра. Равномерный спектр показывает, как частицы могут колебаться относительно года, и эти колебания прослеживаются вправо внизу немножко по-разному. То есть в зависимости от того, сколько слоев, меняются возможности для колебаний степени свободы, и это становится видно на равномерных спектрах. Excuse me, Гамини, which liquid would you use?
So this is a DMF, dimethyl formamide.
Метилформамид.
Yeah, DMF, dimethyl formamide. Okay, so these are some of the electronic properties we have. So usually we use the interdigitated pattern. So then we have Fosforene. So we look at our resistance and resistance change and IV characteristics. So this is how example is connected. If you look at this temperature dependence, you can get your band gap. That also comes very close to 2.2 electron volts. So then also we look at sensor properties. You can see how resistance changes for different gases. You can see for hydrogen, resistance is decreasing. Hydrogen also resistance decreasing. But for argon, it's almost no change. For nitrous oxide, they show increasing resistance. So thus, we know these are good reducing agents. This is a good oxidizing agent. So they show. So then also, if you look at the gate voltage dependence and something called the source drain current, you can see for argon, you don't see much change in your turn-on voltage, but for hydrogen, you can see your turn-on voltage goes much higher. Right? Here, this becomes for hydrogen, that's become. They have the same tendency. This is the source drain in the gate voltage. This is the
Once like that.
No.
Смотрите, мы сделали частички, теперь надо исследовать их свойства. Это транспорт properties, то есть это электрическая проводимость. Структурку видите, встречно-штриховую такую. Вот на нее, видимо, сажается частичка, пропускается, но подается напряжение, исследуется ток, и можно понять, какое там сопротивление или проводимость. Потом это все еще можно засунуть в трубу, пустить разные газы и посмотреть, как проводимость частички будет зависеть от газа. То есть частицы газа на нее садятся, определяется проводимость, а оттуда уже можно вывести ширину запрещенной зоны. Excuse me, Гамини, do you look so?
Yeah, we just disperse it. So just with the liquid, we just disperse and let it dry. So it is maybe not just one, so there may be several. So whenever you make a contact, you have a device. These are like separation is maybe couple micrometers.
Between the
Yes. So this separation is about maybe 2 micrometers.
And you make this structure in your lab?
Yes, it's in the clean room.
In clean room. It's a photolithography.
Yes, these are all photolithography, yes.
Мы можем.
So then also we find some photo response. So this resistance we can see for different lights. So we use red and yellow light. So they show different photo response for that depending on the bandgap, right? So we see different response for different wavelengths. So they have very good photo response for.
It's how resistivity depends on the intensity of light.
Yeah, intensity also we see a slight difference. So not very big, but it depends on the wavelength. Yellow versus red. The intensity we don't see big change. You can see.
And what about other wavelengths?
Yeah, we only tested for two wavelengths. So that shows your band gap behavior. Anyway, so what is interesting in this talk is, so we are talking about black phosphorus, right? So there's a theory, they predict there can be another phase called blue phosphorene. So nobody has, very recently there was one group, they have shown the existence of that blue phosphorus experimented. But theoretically, you can see this is the black phosphorus. Black phosphorus. Remember in the black phosphorus is a different structure, right? So this is also a stable structure. So they have completely different properties. So our proposal is to make this black phosphorus by intercalating lithium and apply very high pressure. So that we did some theoretical calculations. So that shows it can lead to this new black phosphorene. So that's what we got funded to make this new phase of phosphorene, going from black to blue. It's theoretically people have calculated.
It's only one group?
Yes, yeah. Only one Chinese group has shown.
And they have experimental samples or?
Yeah, they have made only very small particle. Nobody could reproduce that result. I'll show you that data also.
Окей. Еще, ребята, видите, бывает другой фосфорен с другой структурой. Но пока только одна исследовательская группа показала, что его вообще можно создать реально как и исследовать. Они говорят, что это можно попытаться сделать с помощью высокого давления и добавки туда лития, и они, видимо, сейчас работают над этой задачей.
You can see for black phosphorus, this is your unique cell here, exogenous unique cell. You know, black phosphorus had a spare unique cell. Right? So that's a completely different structure. So here is the comparison between.
Color is different for lithium and
No, so still this is only phosphorus, no lithium. This is black phosphorus, this is all phosphorus, but you can see the unique cell here. So now unique cell is this is more like graphene kind of structure. This is black phosphorus, this is blue phosphorus. So this is, we know that they exist. So this is still not very clear whether this structure experimentally can exist. So except for one group has shown this one. Okay, so I'll just quickly go to that. So this is the work by this Chinese group. They have shown this small area, but they have done some encapsulated growth of phosphorene. So they find that structure close to this one, so that is more like black or blue phosphorus. So this is theoretical simulation. So this is the only existing results for black phosphorus, sorry, blue phosphorus.
It's experimental picture.
What's that?
It's experimental pictures and
Yeah.
guys from China
Yes, yeah.
have found some
Small areas of black phosphorus. Yeah. Sorry, not black, blue phosphorus. Yes. That's nobody ever has reproduced that result.
Понятно, да, с левой стороны этой картинки экспериментальные, ребята из Китая умудрились найти такие участки на фотографии с атомного силового, где это просвечивающий, в общем, с микроскопа, где похоже, что структура все-таки вот такая, треугольная. но это очень плохо воспроизводится, никто больше пока не сумел такие штуки сделать. И результаты, можно сказать, что это супер открытие, а может быть это фейк, пока еще не знаю.
Гексагональная структура.
Да. Да.
Okay, so that's what we are trying to, this is our proposal. What we are trying to do is start with the black phosphorus, then integrate lithium. So we already showed this one, we recently published the work, just use the lithium integration. So then we apply high pressure. So actually first this one we show by this one with some pressure you can make it go from black phosphorus to blue phosphorus. So this is the blue phosphorus. So this is the proposal we have. So here we show without even pressure there's a possibility, but we find it's not very easy to do this one. At this point we need to have high pressure coming into this one. First intercalate lithium, then apply high pressure. So that can be blue phosphorus.
Окей, это предположение группы, что можно получить голубой фосфор из черного, если внедрить туда литий, а потом поместить это все в очень высокое давление. Возможно, что литий таким образом разорвет структуру, что это станет именно блу. То есть будет иметь вот такую структуру. Is it only a proposal?
Yeah, so proposal is to integrate lithium, then apply high pressure. So that can give you blue phosphorus.
Предлагаю попробовать получить такую структуру.
Okay. So when you talk about high pressure, we are talking about gigapascal kind of pressure. So that means we need to use something called the diamond anvil set. So you have these two diamonds, then you put the material here and apply force from both ends, so then you can get pressure up to like maybe hundreds of gigapascal. So 100 pressure to that. So let me give you a little introduction about high pressure. So if you look at typically, you can get, if you go underground, so when you go, so this is your Earth's surface. If you go inside the Earth, so in about like 6,000 kilometers, your pressure is about 300 gigapascal. That's the kind of pressure we are expecting. But this pressure you can get in the lab using the diamond anvil cell. So, not only that, you can even do at high temperature also. There's something called the laser heated, BAC with diamond anvil cell. Laser heating, so this you can use a laser to heat the material, right? So then you can get high temperature and also high pressure. This is like 300 gigapascal. So we are working in the range of maybe hundreds of gigapascal.
And which temperature?
So we are doing at room temperature right now. So, but we are also, we have something called this resistive heating. Yeah, this one here. This resistive heating is mostly, we have a coil, pass a current, and so we can do around maybe several hundred Kelvin and about 100 gigapascal pressure.
And do you think that the material will be still two-dimensional?
No, so no, because we have to have something called the pressure transmitting liquid. So when you apply that one, pressure is not just touching the one. So we have a pressure propagating medium. That's how the pressure is done. So people have done this high pressure work for other 2D materials. So let me quickly show you. So these are some of the work, other 2D materials people have shown, like for example, this molybdenum disulfide. So at ambient temperature, ambient pressure, they are more like a semiconductor here. So you have this linear temperature coefficient, but when you go to about 15 gigapascal, they immediately change the phase. It becomes metal. So that means it shows, sorry, initially it is showing, yeah, this is a metal and this phase. So this is this way. You can show going from semiconductor to metal phase transition. So under high pressure. So this people have done for other 2D materials. What we are planning to do is for phosphorus, but with lithium interconnection. So you can see how this even graphene or this one going from metal to semiconductor. Even some other materials, people have seen phase transitions happening under high pressure. So this is for other 2D materials. So you can say the phase transition, right? Like semiconductor to metallic. What we are trying to do is going from black to blue phase transition.
Способ примерно понятно. Помещаем все между двумя алмазными граниточками и давим со стороны света. А вот что-то получится. Видимо, на свете где-то есть ребята, которые по-серьезному занимаются именно этим. Берут пирамидочки разные материалы туда и давят. И вот публикуется, судя по всему, нечем подозревать. Так что если у кого-то есть пара алмазов,
Несите алмазы, а мы понимаем, что
Yeah, so this is the experimental setup we have in our lab. So this is a diamond and cell. So then to measure the pressure we use, you have to use something called ruby crystal. Ruby has this, the photoluminescence peak. So under pressure that peak shifts. So from that you can calibrate your real pressure. So then we look at, this is some of the initial results we had for our experiment. So this is the Raman spectroscope. So this is under normal pressure. When you apply pressure, you can see the Raman peak is shifting. All these three peaks, right? We have A1G, B2G, and A2G peak. They all shifting under pressure. So then at the end we are starting to see a new peak. We don't know what it is. So we know definite trend. So but still we have, this is without any lithium, just apply pressure. So our real work is going to be first intercalate lithium, then apply pressure. So we have everything now ready in our lab to do that experiment.
was an in situ experiment.
Oh, all in situ, yes, yeah. So this is our spectrometer, the Raman India ratio, the Raman spectrometer. Yeah. So we have this special optics for the longer working distance. So then everything is done in situ. Apply pressure, take the spectrum, then go to the next pressure. That's how you collect all these different spectra for under different pressure. You can go from, we already went to, actually this is not the real pressure, this is the pressure of the way you work is, you use some gas to pressurize it. So that gas pressure you can calibrate to real pressure. So this is about what we got to almost like 50 GPa. So forget about this one. This is the gas pressure. So real pressure is about we have to about 50 GPa.
Gas pressure.
Yes, when you pressurize it, you have to use some kind of gas, like we use the argon gas. So that pressure will increase the inside pressure.
Inside pressure.
Yeah.
That's for the diamonds.
Yeah, still you are pressurizing it, but with the pressure you can increase that pressure. So that you can do by the ruby luminescence peak.
Вот эта их установка, чудо просто. Они инситу измеряют, то есть прямо вот в процессе эксперимента давят на образец и смотрят на равновский спектр. потихонечку у них стандартные спектры меняются, и вылез в самом верху видите какие-то фики появились, которых раньше не было. Это пока что без лития, но тут уже что-то видно.
Как они идентифицируют? Как они дают? Получается, снизу глазом, что ли?
Да, давление,
А
газы.
сверху что их как можно снимать?
Воды. Когда я
Чем пример?
Да.
Если они оба давят, как они следуют?
Я там похоже уже.
So you have this, yeah. So here you have that opening for the laser to, because this is a backscattering. Oh yeah. So the yes, yeah. This diamond and pixel has optical window here. So you can, because we are looking at the backscattered light, right? You just round it, so then scattered light, still we use the same Raman spectrum. So everything is inside, you can see under the microscope, you have the diamond and inside. So the whole cell is about this tone. But we need to have a gas connector. That's all, most of the pressure coming from there. So once you tighten it one, then you have to use, because that's a membrane. So that's making that high pressure. So you have to increase this outside gas pressure. So you have to go like to 45 bar pressure is like 50 GPa.
And what's the size of Rubik crystal?
Oh, that's very tiny. The whole sample is like very small. So because this is between these two diamonds, right? So this is one diamond, this is other diamond. Then your sample is only. These are very small amount. Then you have to, but you don't have to put the ruby crystal with the sample. You do that as a calibration. First you do with your gas pressure and your PL shift.
First time you put the Rubik.
Yes, yeah. Then you calibrate it. Yes. Then we know this gas pressure and the PL. Then we know PL and the real pressure.
Yeah. Okay.
Yes. So then you have the GPA pressure versus the PL. So from that you can get the real pressure.
Да, мы говорим о том, как они калибровали, как узнать реальное давление в этой вот точке по сравнению с тем давлением газа, который подается. И сначала туда поместили кристалл рубина, у которого сдвигается фотолюминесценция этого давления, и сделали калибровку. А потом, уже зная, какому давлению вот здесь соответствует давление газа снаружи, рубин брали и поместили туда образец.
Yeah. So lastly, recently the Minu in the theory group, so she did the theoretical calculation for this Raman shift in all three modes. So this is A2G, B2G, sorry, A1G, B2G and A2G mode. So this is the Raman shift. So you can see this mode. So then, yeah, so this is the experimental result for two different samples. We have one sample which taken from here. So this is more like a mono layer. So then taken from here, that has about maybe 10, 15 mono layers. So this is the experiment. So actually this one is from the mono layer sample. So that's this result. So then we had exactly somewhat similar results for this sample that has many layers. Minu's calculation was on biophosphorus. So we can see that results matches very closely for this more layer sample. So this is a theoretical result, the solid line. So this is the experimental result. But if you go to monolayer sample, that theory doesn't fit very well. You know, the theory is done for bulk sample. Now she is trying to do for a few layers. This is very encouraging. We are writing a paper on this one with the experiment and the theory coming together.
Говорится о сопоставлении теоретического расчета и экспериментальных измерений. Как эксперимент делается, мы посмотрели, кто-то посчитал, как рамановские сдвиги должны вести себя при изменении давления. И это было рассчитано для балок, подъемный образец, не моностой. И для него все достаточно, видите, неплохо сходится, а для моностоя разница есть.
Yeah. She did some kind of DFT calculations, but applying more like hydrostatic kind of pressure from all three directions. So we calculated the Raman-ship vibrational modes for 3 modes. So this is their theoretical calculation. So this is our experimental data, this dot zero.
Движение сплошное с любым, что не идет и нет, я не знаю, движение сплошное с любым, конечно, материал, все конечная техника.
Okay, this theory is working for continuous medium.
Yes.
If you have quantum effects, like monolayer, it works.
She has to introduce some other parameters into the system. That's why they did the calculation for bulk material. So, monolayer is a little hard to do, but she's trying to do that calculation. Okay, I think that's all I have.
For today.
Yeah. Everything is done inside the glove box.
Okay.
Yeah. So once we do the
What position phosphorene in the liquid? So it's around?
no, so that's what I said. When we do the centrifugation, so always we pick samples from the top one if you want to study the monolayers. If you pick from in the middle, they are like few layers.
So when the liquid one position, we will go, right?
What's that?
When the liquid,
Always if you pick from the top,
it's
yeah, you can see it's kind of color also different here. So then everything is done inside the glove box, that's the important thing. Then we assemble the albumin cell also inside the glove box. We cannot expose to air. So then under that argon glove box, so then we take it to the Raman spectrometer.
if it's several layers, it's the same number.
Yeah. So they all are stacked. Like phosphorus is always layered structure.
Я спрашивал, когда он рассказывает про исследование сопротивления, электрические свойства, вот эта вот жидкость, которую он переносит, как в ней позиционируются вот эти вот фосфорные слои. Что-то он, я подумал, что там он удобно как-то, а на самом деле, то есть когда они получают вот этот эффект, сверху там монослои, снизу монослои, то есть они этой капелькой берут, и она кладут на какую-то поверхность, и она получается параллельно как графитовая слой. То есть она не как-то там вот так светит или вот так, и они параллельно. Ну, например, они знали, если это электрические свойства. То есть там мы знаем, что это сушит. Почему это сушит?
Well, we need to have the liquid because when you do this diamond albumin cell, materially you need to have some kind of liquid like pressure transmitted media. So that's also we use the same that DMU. That's a nice thing. You take it from the liquid here, then put it here, so then you have that medium also. Like Victor said, if you don't have medium, you will just crush the two.